So, hello students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. I am Dr. Raman Kapoor, Associate Professor at ABES Engineering College, Ghaziabad. This is lecture number 11 for this subject. From this lecture onwards, we are going to shift our focus completely towards the device side of things. Okay? So, we are going to start a very vital topic known as p-n junctions. So, whenever we talk about p-n junction, the first thing which might come to mind of any reader or student is that we are talking about a two terminal diode. Okay? But we should not limit our thinking and our analysis to only to a p-n junction diode, but we should consider or analyze a p-n junction as a sort of a circuit arrangement which might be present in almost every semiconductor device. Major semiconductor devices or most of the modern electronic devices have at least one p-n junction included in its structure. Okay. So, the way the devices are fabricated, they are bound to have one or multiple p-n junctions at different locations. So, we must know all the analysis and all the electrostatics which is associated with these kind of junctions, because these electrostatics are going to form the basis for analyzing major semiconductor devices to follow. Okay. So, if I want to define or describe about p-n junctions, I would say that these junctions are quite important for all modern electronic applications and to understand the underlying behavior of semiconductor devices. The p-n junction theory serves as the foundation of the physics of major semiconductor devices. A p-n junction by itself is a two terminal structure. Okay. So, you will have one connection or one way to access the p side of the semiconductor, p side of the junction, and you will have one terminal or one metal connection to access the n type region. Okay. And depending upon what doping has been done either on the p side or the n side or both the sides, how is the device geometry, how the biasing has been done, a p-n junction can be exploited to perform various different functions, and that is our main objective from now on, to study how this junction behaves. Okay. So, we make a small initiation here. We say that all our analysis is based around what is known as an abrupt junction. Okay. When we say abrupt junction, see, whenever we are talking about the junction, it means that it is going to have two different types of materials on either side. One side of the material is a p type semiconductor which has majority holes, minority electrons, and has lot of negative acceptor ions. Other side of the junction is an n type semiconductor which has majority electrons, minority holes, and a lot of positive donor ions. Okay. Whenever we are transiting from one region to another, we are saying that this kind of transition is very sharp, it is very abrupt, and it is not graded. Whenever we are crossing the junction, we are switching from one type of doping to another almost immediately. So, if you are moving from p side to the n side, okay, if you are moving to the p side to the n side, okay, so this left side is your p region and this is your n region. If you are moving from left to right, just crossing the junction, you will cross from p type doping to n type doping, and whenever you are moving from right to left, just at the instance of crossing this junction, you are moving from n type doping to p type doping. So, just right to this edge there will be no acceptor ions, only donor ions. Just left to this junction there will only be acceptor ions and no donor ions. This kind of an assumption or this kind of an arrangement greatly helps in easing the analysis of p-n junction. Okay. All the electrostatics associated with the p-n junction become quite easy and simple when you assume that you are working around an abrupt junction. It is easier to write the equations, it is easier to identify boundaries and limits to the mathematical analysis. Okay. So, this diagram on the slide which you are seeing is basically showing you the energy band diagram. Okay. We have seen energy band diagrams before, you have drawn energy band diagrams of a p type semiconductor. Okay. There the Fermi level is closer to valence band, further away from conduction band. In an n type semiconductor, your Fermi level is closer to the conduction band, farther away from the valence band. Okay. When you combine these two regions, the major underlying is that the Fermi level on either side has to be continuous. If that does not happen, that basically means that charge neutrality or equilibrium has not been achieved as yet. Any gradient in the Fermi level would cause a diffusion of charge carriers until this Fermi level aligns. So, in an unbiased equilibrium case, the Fermi level is aligned on either side of the junction, whether it is p side or the n side. Okay. So, if I see, just focus on the left and the right side of this box here. Okay. So, this is the middle region, this is the depletion region. We are going to start our analysis on depletion region shortly. See this region on the left side, this is your p side, okay, and this is your n side. So, you can observe that Fermi level is close to valence band, intrinsic Fermi level lies in the middle, and the Fermi level is quite far away from E c. This is what a p type semiconductor looks like. Similarly, for n type you would see that the Fermi level is closer to E c. So, this is your E c, this is E v, and this is your intrinsic Fermi level, okay. And this level which you see here, this is the Fermi level. Okay. And this is how an n type semiconductor looks like. You have lot of electrons, so higher probability of locating an electron. In the middle you would see that to maintain this continuity, the bands have to bend. Okay. So, while transiting from p to n, the bands bend downwards, or if you are transiting from n to p, the band bending seems upwards. So, for electrons to move from n to p, they have an uphill barrier. So, they have a potential barrier to climb. Okay. This barrier acts or plays a very important role when we study the working of a p-n junction, and the level of this bending, basically measures the height of the potential barrier. Okay. So, this is how the energy band diagram of a p-n junction looks like. Now, we want to study this middle region which I was just talking about on the energy band diagram. What happens in the region very close to the junction? Just few dimensions to the right, few dimensions to the left, whatever actions is happening is generally happening at the interface. Okay. Whenever we combine p to n region or p and n region together, when we say combine, we basically mean that if you have one type of semiconductor, say p type, you diffuse opposite type of impurities, that is pentavalent impurities deposited on a p type semiconductor. This will cause opposite type of doping to be developed, and a junction will be created between a p type and an n type semiconductor. Whenever such a junction is created, the first thing which happens is the process of diffusion. Diffusion always occurs whenever there is a concentration gradient. Whenever a particular region has high concentration and another region has lower concentration, charge carriers are going to flow from higher to lower region, lower concentration region. So, here when we create this junction, the p side has lot of holes, n side has very few holes. N side has lot of electrons and p side has very few electrons. Because of this, there is a concentration gradient for both holes as well as electrons. So, holes start to diffuse from p to n, electrons start to diffuse from n to p. Okay. This is the first thing which happens, that the diffusion starts to take place. Whenever this diffusion occurs, at the junction these charge carriers meet, and whenever an electron meets a hole, it recombines, it annihilates, and the charge carrier is lost. So, just at the region very close to the junction, there is going to be a very high level of recombination of charge carriers taking place. Okay. So, a lot of charge carriers will recombine with each other. What will happen is that the region very close to the junction on the p side, this will uncover or expose the acceptor ions on the p side. On the n side, this will uncover donor ions. Okay. So, then after this recombination has taken place, we would come back to our abrupt junction. This is how the junction is going to look like. The region just close to the left side, just close to the right side will be depleted of free charge carriers because they recombined. Okay. So, holes were moving here, and electrons were moving here. They met at the junction, recombined and exposed your immobile ions. So, now at the region very close to the junction, you have negative acceptor ions here and positive donor ions here. This sort of creates a potential difference, because you have positive potential here and you have lot of negative potential here. Okay. This accumulation of charge creates potential, because there is two types of charges. So, it is a potential difference, a voltage has been generated. This voltage is known as built-in potential. Because there is a voltage across a finite distance, there is a voltage gradient. So, from here you are moving from minus to plus. So, there is a voltage gradient, which means inside the depletion region there is an electric field. Okay. Now, this electric field is in this direction, positive to negative. Holes were moving in this direction. So, this electric field opposes further diffusion of charge carriers. Okay. So, this depletion region once formed is going to oppose further diffusion. Okay. So, it is going to oppose further diffusion. If this does not happen, the charge carriers will keep on diffusing on either side, because even at this stage the concentration gradient exists. Okay. So, diffusion can still take place, but because of this inbuilt potential, built-in potential or then intrinsic electric field, there is opposition to further diffusion. Okay, and charge carriers are left in the bulk of p side and bulk of n side. Okay. This region, which is depleted of free charge carriers and only has immobile ions, acceptors on the p side, donors on the n side, this is known as the depletion region. This depletion region can be modulated in many ways to produce different kind of devices. Okay. So, this graph which or the image which you are seeing basically tells you various different distributions. So, you can say that on the p side you have lot of holes, concentration reduces, on n side you have lot of electrons, then concentration reduces. Okay. So, gradient is still there, but further diffusion is stopped because of positive charges here, negative charges here. These are not free charges, these are immobile ions, too heavy to move. Okay. This generates a potential. Okay. And this depletion region is also known as space charge region. Okay. It has different names, space charge region or depletion region. Okay. So, if you see, this is your charge density with respect to distance, you will see negative acceptor ions here and positive donor ions here. Electric field in the bulk, there is no potential difference. Okay. So, positive negative charges balance each other, there is no potential difference, gradient is present. So, there is no electric field. In the bulk of p side, bulk of n side, electric field is 0. Whatever electric field is there, it is in the depletion region, and the maximum magnitude of electric field is obtained at the junction, okay, at the meeting point. Similarly, the potential, it is constant in p side and constant in n side, and it has a gradient in the, it has a gradient from negative potential to positive potential in from p to n. Okay. This x axis which you are seeing here, we say that the junction is our origin. Okay. The right side, the n side is your positive x axis, the left side or the p side is your negative x axis. Okay. So, the depletion region has two halves, one on the p side, one on the n side. The p side of the depletion region lies along the minus x axis, okay, and the n side of the depletion region lies along the positive x axis. This axis orientation we use for further derivations as well, right. So, now we want to know what are the various electrostatics associated with the depletion region. As we have already said, p side has negative acceptor ions, N side has positive donor ions, this results in the potential difference. This is known as built-in potential, and now we need an expression for it. Okay. This is also known as contact potential, space charge potential. Okay. So, there can be different names, but it is the same thing. Symbols can be different, it can be represented by VBI, psi bi, V naught, okay. But we are talking about the same potential barrier across the junction. Okay. So, now I want an expression for it. Till now we have not applied any voltage or a bias to the PN junction. So, my PN junction currently is in a unbiased condition. It is at thermal equilibrium. So, net there should be no current flowing across, okay. But diffusion was taking place, it created an electric field. So, a drift current can happen. So, there can be a diffusion current as well as a drift current, but because it is unbiased and at equilibrium, these two currents should balance each other. So, this is your drift current. I am taking the example of holes, you can do the same with electrons also. Okay. So, drift as well as diffusion, these currents add up. This is the expression for drift current, hole drift current. This is the expression for hole diffusion current. They add up to 0. Okay. You can take this term here, Q will cancel, you can take mobility here. So, this is the equation you are going to get. This is nothing but Einstein relation, d by mu equal to kT by q. Okay. Electric field can be defined as minus dV by dx, right. This is hole concentration, this is hole concentration gradient, right. So, minus dV can be written as Vt, here Vt is your thermal voltage, okay. This is thermal voltage and it is given by Boltzmann constant times temperature divided by Q. As per Einstein relation, it is equal to d by mu, okay. Whether it is holes or electrons does not matter. D by mu is equal to kBT by Q, which is also known as thermal voltage, right. Now, to get the expression for voltage, because this is dV differential, I need to integrate. So, I integrate both sides and just see what the limits I am setting. When I am moving from the P side of the depletion region to the N side, on the P side say the potential is Vp, okay. So, I name the potential Vp. On the N side, by the time I have completed the traverse the whole depletion region, potential approaches Vn, okay. So, I will just go back again to this graph. This is the last graph is for voltage, okay. So, this is x, this is V. If this is my depletion region and the junction, on the P side I am saying that the potential is Vp and on the N side it is Vn and it rises, okay, from negative to positive potential. So, these are my limits of integration from Vp to Vn. And when I am moving from P to N side, how is the concentration varying? In the P side, holes are in majority. So, I say hole concentration in the P side. When I reach the N side, again holes become minority charge carrier. So, I have hole concentration on the N side. So, I write it as P subscript N. This is hole concentration on the N side. Then I integrate, integration of 1 by P gives you natural log of P. Okay. So, and Vn minus Vp is nothing but your total built in potential. Okay. So, potential is constant in bulk of N side, constant in bulk of P side, only transition takes place in the depletion region. So, this is your built in potential. Okay. You can get rid of this minus sign by simply reversing this. Okay. So, I can write V naught equal to thermal voltage kT by Q, which is hole concentration in P side divided by hole concentration in N side. Holes in P side are majority charge carriers, only doping dependent. Holes in the N side are minority carriers, can be obtained by law of mass action. So, in the P side, hole concentration is equal to doping density. In the N side, hole concentration is obtained by law of mass action. Putting all these things together, this is your expression for built in potential. This is the potential barrier which electrons have or experience while transiting from N to P. Okay. So, you need to apply this much of a potential when you are biasing the diode, so that you get excessive current from a diode. Okay. So, this is the expression for built-in potential. Let us move forward. Because there is potential, because there is a finite width, because potential is varying with x, there is going to be an electric field. This electric field is only present inside the depletion region. In the bulk of p and n side, there is no electric field. Okay. For getting the expression for electric field, I am going to start with Poisson equation. Poisson equation is del dot E equal to rho by epsilon. Rho is charge density. Okay. Epsilon is your permittivity, okay, medium dependent. So, if you are going for silicon diode or a silicon p-n junction, you would use the dielectric constant of silicon multiplied by permittivity of free space. Del operator is nothing but d by dx operator. So, I can write dE by dx. Charge density is q times doping or concentration. Okay. So, charge q times carrier concentration is going to give me charge density. Sources of charge can be hole concentration, electron concentration, positive donor ions, negative acceptor ions. So, positive charge minus negative charge is my total concentration multiplied by q gives me total charge density. Okay. So, P minus Na plus Nd minus N. Depletion region is called depletion region because it is depleted of free charge carriers. So, P and N are 0 inside the depletion region. Why only depletion region? Because electric field is only present inside the depletion region. So, I only use the doping densities. Okay. So, dE by dx can be written as, there is going to be another term q here. Okay. Now, the p side does not have donor ions and the n side does not have acceptor ions. To get the total expression of electric field, I need to first analyze for the p side of the junction, then the n side of the junction, and combine these two and you will get the net electric field. So, on the p side you only have acceptor ions, the minus sign is coming from here, this minus sign is coming from here. Okay. So, Nd is 0 on the p side. So, expression becomes like this, and this I have integrated this equation. Okay. So, this I have integrated to integrate this for electric field. Okay. So, on the p side this is the expression, for the n side Na becomes equal to 0 and q Nd by epsilon s comes here. Okay. So, when I integrate, now there is no limits here. If there are no limits to integration, a constant will be generated. To get the value of this constant, I am just going to look at the edges, p edge and the n edge. At the p edge electric field is 0, at the n edge electric field is 0. Okay. So, at x equal to minus xp, electric field is 0. This helps me in getting the value of Cp. Okay. So, the electric field in the p side of the depletion region is this, where xp is the edge of the depletion region on the p side. This is from where the depletion region starts from p to n. Similarly, for electric field in the n side, I get a constant Cn at x equal to xn, again E is 0. So, this helps me in getting the value of Cn. When I combine, this is the electric field I get at the n side of the junction. Xn is where the depletion region ends on the n side. Okay. So, from minus xp to plus xn is my total depletion region. The peak happens at the junction at x equal to 0. So, in this expression and in this expression, if I put x equal to 0, that is the peak electric field. Okay. So, this is the expression for electric field across a p-n junction. Finally, we need the expression for the depletion region also. So, you have a potential, you have an electric field and you have a finite width. For this, we say that the charges on the negative side or the p side, the negative charges, negative acceptor ions, they produce some charge. This is balanced by the positive charge on the n side. So, Qp is equal to Qn. Okay. So, charge on the p side is equal to charge on the n side. How much charge is there on the p side? So, you have Q, area times width is volume, Na is number of charges per unit volume. So, this is the number of charges per unit volume. multiplied by volume gives me total charge. Each charge is equal to charge of an electron basically. So, you multiply with Q. Okay. Remember that acceptor ions, each atom accepted 1 electron. For donor ions, initially each atom donated 1 electron. So, each ion whether acceptor or donor will have charge of 1 Q. Okay. So, this is how you get the charge on the p side equal to charge on the n side, and this is the ratio you get. This basically also tells you if you increase doping, you reduce the width. If Na increases, Xp reduces, if Nd increases, Xn reduces. So, whichever side you increase doping, you reduce the width. Okay. So, with this expression, we know that electric field is equal to minus dV naught by dx. Okay. So, you integrate this across the depletion region from minus Xp to plus Xn, integrate this. This is your built-in potential. We know that electric field is on the p side as well, n side of the depletion region as well. So, you split this integral into 2 parts. This is p side and this is n side. From minus Xp to 0, p side, from 0 to Xn, n side. And we have the expression also we have just derived for Ep and En. Substitute these expressions here and you are going to get this integral, simple integral in x. When you integrate this integral and you have the limits also. So, you just simply integrate and put the limits here. This is the expression you are going to get. This is for V naught, built in potential. This we already know. Substitute this in this expression. This is the value you are going to get for V naught. Xp plus Xn, p side of the depletion region plus n side of the depletion region, add them together, this is your total depletion region width. I still have Xn to be eliminated here. To eliminate this, I am going to use this expression again. For Xp, I am going to write total width minus Xn. Okay. With this, I am going to get the expression for Xn. This substituted in this equation here is going to give you an expression for V naught. Just a simple mathematical arrangement either side is going to give you the expression for depletion region width. Okay. So, with this we have ended all the electrostatics associated with the p-n junction. This is just a brief summary of what we have done in today's lecture. This is built-in potential, electric field on the p side, electric field on the n side, maximum or peak electric field at the junction, depletion region width, p side of the depletion region, n side of the depletion region. Okay. These are some of the references you can refer to for the content of today's lecture. Okay. So, with this we end this lecture and we will continue our discussion in next lecture. Thank you.